Let's put all of everything that we have learned so far for isothermal reactor design in comparing the calculations for a single CSTR or when we arrange them in series and parallel. Let's continue with the example with the production of ethylene glycol. This is a follow-up from a previous example where we use a batch reactor to calculate the specific rate of reaction. I recommend you to right now pause the video and gather the information that I'm presenting right now. Okay, so in this system, right, we have a CSTR reactor. I'm just focusing my attention in this particular area of the statement. So we have a system where we have two flows of the reactants. One flow contains the ethylene oxide, and the other flow, the ethylene oxide in a aqueous solution, and then you have a flow containing the water mixed with the catalyst. In this case, the catalyst is soluble in water. It is the sulfuric acid. So one of the things that the statement indicates, right, is that the production of CE is desired to be 200 million. This is a scale-up system or design or process design. The other thing is that the temperature is constant. The concentration of the aqueous solution of A equals to 16.1 moles per decimeter cubed. The stream is mixed with equal volumetric solution of B containing the catalyst. This is going to be important later to do some of the assumptions and calculations. They are fed into the reactor and then mixed, right, at some point. And the specific rate equals to 0.311. If you notice, this specific rate equals to the same one that we did with the batch reactor. So in some sense, you know exactly what will be the temperature that you're going to keep the reactor constant because you're trying to use the same specific rate that you used previously or the conditions that you used previously to calculate. Okay, so we are interested to determine the CSTR volume for our 80% conversion. This is very similar to the examples that we have done before. Then we're gonna have some fun, right? Calculating conversion for reactors that are arranged in parallel, and then compare that to reactors that are arranged in series. Let's focus on part A for this example. As we have mentioned before, Fogler has a great method, right, to put together the analysis of the reactor design. The chemical reactor engineering method includes the mole balance, the rate law, the stoichiometry. We combine the information that we have from the previous steps and then we evaluate. So let's start with the mole balance. We know that this is a CSTR, therefore the volume for that CSTR equals to, right, from the mole balance to this. Remember that for a CSTR, the rate of reaction, it is inside the reactor equals the rate of reaction in the exit condition. That's why we say that CSTR is typically operating at the lowest rate possible for the reactants, right, that are within the reactor. The rate law for this problem, we mentioned this in the previous example for the batch reactor, is considered to be a first order reaction because the water is in excess, and we analyzed this previously. In the stoichiometry, we can get from the table, right, that for a system that is liquid, we can assume that the volumetric flow rate, right, equals to, is constant throughout the whole process. Therefore, right, we can define the concentration in the exit as follow, and solving it more, or substituting or expressing it in terms of conversion, we get the following. Okay, for the combination, we need to combine what we have from the previous steps. So we go back to our definition of the volume. We found out that FA0, right, over CA0, 1 minus x. Okay, we can simplify this, right, by combining these two terms, right? If we divide them, we end up having that the volume can be simplified as follows. Okay. So now we are in the step of evaluation. Remember that this is where you have to decide based on the provided information what method you're going to use. For a CSTR, we know that we just need to evaluate an algebraic expression. This can be done either numerically or analytically to determine the reactor volume. Or if we're talking about a batch reactor, it will be the processing time. Or if we have the volume, it could be the conversion. So because the information that we have here is just data, right? Specific parameters are given in the condition, there's no data. We don't need to use numerical methods, right, to analyze or the area or under the curve for a flow reactor, or in this case for a CSTR, the area of the rectangle, right, that we will have in the curve. So here is you decide what to do. Basically, I think this is one of the most important parts when analyzing and getting the information for a reactor design, that you decide what to use. So from this definition of the volume, we need to get the initial volumetric flow rate. The conversion was given, right? It was 0.8. And they also give us the specific reaction rate. So for the initial flow rate, we know that it's a liquid system, so there's no variation with pressure or with pressure. So here we can say, right, that the initial volumetric flow rate equals to the initial flow rate over the concentration. The concentration of A was given in the statement. However, we need to get the initial concentration of the species A, and we can get this by relating how many pounds, right, are produced of species C, and using the stoichiometric definition of the flow rate to actually relate the flow rate of C with the initial concentration of A. This can be expressed with the following relationship, right? So we're trying to get the initial concentration of A, and we're trying to get that information in terms of mole per second. So what we're going to just do is convert the amount produced of ethylene glycol, which is a species C, and we're just going to do a simple unit conversion. I'm not going to get into the details, but basically you need to just convert from pounds per mole, converts from pounds mass to moles of ethylene glycol, and from years, right, divided by years, but from years to seconds. Okay, so yes, you may need to get information about the molecular weight, right, of ethylene glycol to be able to do this conversion. Anyway, so we get, after we do that this is the volumetric flow rate. Therefore, we can evaluate the initial concentration of A as, notice that we did this evaluation at 0.8, right, conversion of A. So that means that we can evaluate the initial volumetric flow rate of A. Remember that the concentration A01 was already given in the statement. So putting the the numbers right for this and we get that the volumetric flow rate for A equals to decimeter cubes per second. Okay, so remember that it was given in the statement that the volumetric flow rate of A equals to the volumetric flow rate of B. It was the same, right? It was split the same before entering the reactor. So that simplifies, right, the problem, and that means that we can calculate the total, right, initial volumetric flow rate as the addition, right, of the volumetric flow rate for each species. If you plug the number in there, you can get that volumetric flow rate equals to 7.2 decimeter per second. So given that the specific rate was given as 0.311 1/minutes, we can convert that to second just to be consistent with the rest of the units. And then we can get our volume definition and substitute all the numbers. And if you do that, you can get units of meters cube, or you can convert that to feet cube, or in our case, we're gonna use gallons because the statement or the volumes that we're going to use in the next samples are in terms of gallons, just for the sake of comparing the information between all the parts of this problem. Okay, so now let's focus on part B. We're trying to get the corresponding conversion, right? When we have a system with two CSTR in parallel, they are giving us the volume of each of the reactors. We calculated before, we know, right, that the total volumetric flow rate is just the addition of the individual flows. We calculated that previously, so it's there in the drawing. So let's find out how much we can, how much the conversion increases or decreases. We want to see what is the effect of having this array of reactor. So let's start. So using the CRE method, we can get the volume of the CSTR. This is exactly as we did before, with the mole balance, then comes the rate loss, stoichiometry, and all those steps that we used before. So I'm not going to do that right now. If we divide by the volumetric flow rate, we get that the tau can be defined as the total volume over the volumetric flow rate, initial volumetric flow rate. And if we substitute the volume into this expression, we get and rearrange and solve for the conversion, we get the following expression. If you look at it, you can see that you have the definition or the expression for the Damn-Color number for a first order reaction. The other thing that I want you to look at is that here, when we talk about the volume in this tau expression, we're talking about a total volume. However, because we are talking about a split system with equal volume, we have two reactors with 800 gallons, we can say that the total volume that is actually is containing the reaction with that initial flow rate coming in can be calculated as a total volume, like a really, really big reactor, that the volume is double the volume of one single reactor in this parallel system. So therefore, if I substitute this here in this expression, I can get the value of tau. I'm just gonna substitute everything and make sure that because the volume is given as 800 gallons, you have to convert that back to decimeter cube. And we get that tau. I'm just gonna do the 800 gallons over, 800 gallons times 2, right? And then I do the conversion, 3.785 decimeter cube over gallon, right? Times 1 over the total volumetric flow rate, and we calculate that previously to be 7.24 decimeter cube per second. Okay, so if we do the calculation, we end up having second. So this is the specific resident time, right, in the reactor, the tau for this particular reactors. Then we're going to move on to calculate the damp color number and calculate the conversion for each of the reactors. If we calculate that damp color number, as you see here, is 4.35, and calculating the conversion, we end up having 0.81. I want you to remember that previously we saw one reactor with a first order reaction, and the conversion for that reactor was 0.81. 0.80, I'm sorry. So you can see that there's not a big change when we divide two flows to two CSTR in parallel. The overall conversion was pretty much the same as the single CSTR. So now let's do the CSTR in series to see if we can improve conversion for this reactor. So let's view when we have CSTRs in series. We have seen this before in the class. However, let's use it, right? Because we're incorporating now the use of the damp color number, and let's see and walk you through all the process on how to solve reactors in series. So I want to gather the information that we have right now. Remember, when you have reactors in series, position along the reactor volume or where the reactants are passing through is important, right? So from the calculations that we obtained previously, we already have the initial flow rate, the initial volumetric flow rate. We can get from stoichiometry the flow rate at position 1. We need to get the concentration at that point, and then we need to get the concentration, not the concentration, the conversion at point 2 and point 1. Also, we need to get from stoichiometry the definition of the flow rate at that position. And remember, it is important that you know exactly where you're performing your mass balance, your mole balance, because you need to have as a reference the correct position. So for the first reactor, the mole balance is going to look very similar to the one that we have done before. But for the second one, you have to make sure that you have position 2 and comparing position 1 in terms of the ins and outs for the reactor. So let's start working this problem. So let's think about what will be your prediction. What do you think is going to happen with the conversion, right? Comparing a parallel reactor, a single reactor, and now that we have two reactors in series. Think about it, write it down on the corner of your notebook, and let's go back again, okay, to it. So for the first reactor is similar to what we did already. We can get an expression for conversion, right? Equals to this. So for the second reactor, right now we have to be very, very careful about the subscripts and where are we in relationship to those positions. So remember, from the general mole balance, we get that the volume of the reactor is the difference between the flow rate, right, in and out from coming from that specific volume, divided by the rate of disappearance of A at the point number 2. Okay, that is important, right? We're talking here at point number 2, which is different as the one in point number 1 that correspond to the first reactor. So we know that the rate law is first order, but now we're looking at concentrations in the second position coming out of the second reactor. So for the how you call it, for the flow rates, right, we can do in and out, right, pretty much of the on that specific position. We have the definition for the flow rate at point 1, and then we can define flow rate on the exit conditions in the reactor number 2. So now let's combine all this information. So now if we combine this information, we see that first we need to, once we define the rate law, we need to substitute the concentration at point number 2 here. And we substituting the values, we can get an expression for the rate law in terms of the concentration at point 2. If you substitute both the difference, right, between point 1 and point 2 and point 0 and point 2 and I'm sorry, point 1 and point 2 over the rate of reaction point 2, you can get an expression like this. Okay, this cancels if you see. So as a standard procedure, right, when you try to state the conversion for any of the reactors, we are trying to use the Dampf-Color number, right, to simplify the mathematics, and also because the Dampf-Color number is very characteristics and tell us information about the actual reactor and the reactor flow. So to do that, you always divide that volume that we were obtaining over the volumetric flow rate to get tau, and then solve for x2. I recommend you and ask you to have fun and do the algebraic calculation to get to this expression. If I calculate the Dampf-Color number and substitute in this equation, I can see that for x1, which is this expression that we use, and for x2, these are the corresponding conversion for this system. And it is very clear to see the effect of having one single reactor or having parallel reactors, or now having a series of reactors that are CSTR. You can see that when you have two CSTR in series, the overall conversion is substantially greater than the one for a parallel reactor or a single reactor, which was 0.81 or 0.1 and 0.1 respectively. So these results are typically common for isothermal reactions, and also for power laws that are typically greater than 0. If your power law is not equal to 0, like the order of the reaction is not equal to 0, you just need to follow the same steps that we have done so far to come up with a statement, right, or a definition of the conversion based on that rate law.